Now, we said that for a given reaction at a given temperature, okay, the value of the reaction quotient approaches a constant value, the same value every time when it reaches equilibrium. So that value that it approaches is called the equilibrium constant. We call it K or KEQ. Okay, so that's a constant at a given temperature for a given reaction. So if you have Q, okay, Q can be at any given time, whether the reaction is at equilibrium or not, you can calculate Q. But once the reaction is at equilibrium, it will always have that same value for a particular reaction at a given temperature, and that value is going to be equal to KEQ. Right? So let's look at an example here. How do we determine the KEQ? You can basically just carry out the reaction, okay, and determine the activities of the reactants and products at equilibrium. Let the reaction go all the way until it stops, until it reaches equilibrium. Then measure the activities of the reactants and products. So let's illustrate that with this simple example. Let's say you have X. 1 mole of X yields 3 moles of Y in aqueous solution. You let this reaction go to equilibrium. Okay, let's say you start off with a mixture that has 0.1 molar X and 0.1 molar Y to begin with. So the activity of X is zero point 0.1, activity of Y is 0.1 at the beginning. Okay? You mix some X and Y. And then you let it run until it reaches equilibrium. Okay? How do you know it's reached equilibrium? When the concentrations of the reactants and products are no longer changing, right? So you find a way to monitor the concentration of X or monitor the concentration of Y. So let's say the reaction has reached equilibrium, and by the time it's reached equilibrium, the concentration of X is only 0.05. Okay, what's the KEQ for this reaction? What we can do is we can construct what's called an ICE table. It's a very convenient way of doing this. So X, okay, aqueous, yields 3Y, aqueous. And you make a table. Start off with an initial concentration. What's our initial concentration of X? 0.1, right? And what's the initial concentration of Y? Also given in this problem to be 0.1. Okay. What would be the changes? If the reaction were to go forward, first of all, did this reaction go forward or reverse? I ended up with, let's look at the equilibrium values. My equilibrium value for X is 0.050. What happened to my X? It dropped from 0.1 to 0.05. By how much did it drop? Point, what? 0.050, right? Okay. So if I lost 0.050 moles per liter of X, how much Y did I make? If I were to lose X moles of X, how many moles of Y would I make? 3:1, the balance equation. So I'm going to make 3X moles of Y per liter. Okay, if I lost X moles of X per liter, then I'm going to make 3X moles of Y per liter. So what's the change in Y going to be? It's going to be plus what? 3 times 0.05, right? Because we can identify that X is 0.05. So how much Y do I have now? It's going to be 0.100 plus 3 times 0.05. Okay? So we're assuming we have a liter of solution. So these are the moles in that 1 liter of mixture. So what's our reaction quotient? Initially, what's our reaction quotient? How do I calculate reaction quotient? Concentration of Y cubed over concentration of X, right? Remember, products over reactants. So what's the concentration of Y? 0.100 cubed divided by concentration of X is 0.100. So what is my Q at the beginning of this reaction? Initially, my Q is 0.01. Okay, 0.0100. What is my Q at equilibrium? Zero zero one. So it's 1.00. Okay, 1.00 times 10 to the negative 4. Okay. So what's my Q at equilibrium? This is 10 to the negative 2 cubed over 10 to the negative 2. That's 10 to the negative 4. Oh, it is 0.1. Oh. Oh, it's 10 to the negative 1 over 10. So it's 10. I had it right. Okay, so it's 10 to the negative 2. Okay. All right, so it's 10 to the negative 2. What's my Q at equilibrium? What do I have at equilibrium? This one right here. That's my Y at equilibrium, right? So that's going to be what's 0.1 plus 3 times 0.05? 0.25? Okay, so this is 0.25. Okay, 0.250 actually. So 0.250, so I have to cube that. And what's my denominator now? It's not 0.1 anymore, it's now 0.05. So divided by 0.05. So what's 0.25 cubed over 0.05? 0.25 raised to the power 3 divided by 0.05 equals 0.3125. Okay, so 0.3125. So that's 0.31, right? 312. This is going to be what? 0.0100. So what happened to my Q? From 0.01, it went up to 0.313. It went up or down? You can see that as this reaction goes forward, you're making more numerator, right? You're making more products. Your Q increases. Okay? And so what's the KQ for this reaction? Is it 0.01 or 0.313? You're asked for the equilibrium constant. Okay? What's the KEQ for this reaction? Is it A? Let's see if you've been paying attention. Is it 0.01 or is it 0.313? That's the KEQ. Okay. Correct answer is 0.313. That's the value of Q at equilibrium, right? And it's going to stay there forever unless you disturb your system. You do something to it. It's reached equilibrium. That's the value of Q. So for as long as you're looking at the same reaction, for that particular reaction at that temperature, that would be your equilibrium constant. Okay, so it's pretty straightforward.